Programming is a multifaceted skill that demands a combination of knowledge and practice to master. To enhance your coding proficiency, one of the most effective methods is to solve classical programming problems. These well-known challenges have been used for a long time to cultivate programming skills and are ideal for sharpening your problem-solving abilities. These problems span a diverse array of topics, ranging from elementary programming concepts to intricate algorithms and data structures. By tackling these challenges, you can expand your programming repertoire, develop a deeper understanding of key programming principles, and improve your ability to design efficient and effective solutions to complex problems. Today, we will try to find the largest prime factor in number n. Before we proceed, let us acquaint ourselves with few terms. First term we need to understand is prime number. A prime number is a positive integer greater than 1 that has no positive integer divisors other than 1 in itself. In other words, a prime number is a number that is only divisible by 1 in itself. For example, the first few prime numbers are 2, 3, 5, 7, 11, 13, and so on. Prime numbers are important in mathematics and computer science, and they have many applications in cryptography and number theory. Next, what is a factor of a number? A factor of a number is an integer that divides the number exactly without leaving a remainder. In other words, a factor is a number that can be multiplied by another number to get the original number. For example, the factors of 12 are 1, 2, 3, 4, 6, and 12, since these are the numbers that divide 12 exactly. Factors are important in mathematics and are used in many different contexts, such as finding common factors between numbers, simplifying fractions, and factoring polynomials. Using the knowledge from previous two slides, a prime factor is a factor of a number that is a prime number. In other words, a prime factor is a prime number that divides another number exactly. For example, the prime factors of 24 are 2, 2, and 3, since 2 and 3 are both prime numbers and they multiply together to give 24, 2 by 2 by 3 equals 24. Prime factorization can be used to find the greatest common divisor, GCD, and the least common multiple, LCM, of two or more numbers, and it is also used in encryption algorithms such as the RSA algorithm. We will start by looking at how we can check if a number is a prime number. We will then move on to learn how we can find all the factors of a number. With this knowledge, we will learn how to find the prime factors of a number, and finally we will learn how to find the largest prime factor. For each step, I will be sharing various techniques to either share a concept or just some optimization. These are not the only ways to solve these problems, and I am confident, once enlightened, you will try your own versions. There will be timestamps in the video and you may jump around. I would recommend you to watch the whole video to learn few interesting techniques. Let us get started. I am going to use C# language to write these programs. You may use any language that you are comfortable with. This series is more about problem solving and algorithms. Of course, I will share few things particular to C# language that may help people learning C# language. I will not type the whole code, to not make the video very long. The very first thought that comes to our mind is to divide the number n by all the numbers starting from 2 to n-1. The reason being that 1 is a universal factor and we don't want to check for n itself. We know that n will always exactly divide n. So, if any number is able to divide n exactly, then n is not prime, else n is prime. So, our function may look something like this. As mentioned, we write a loop starting from 2, going up to n-1, and we keep on trying to divide n by I. And if there is any value of I that exactly divides n, we return a value of false. Otherwise, if the loop gets over, we return a value true, indicating that no number could exactly divide n. Now, we apply a little bit of mathematics. As the smallest factor of any number can be 2, it also means that a number n cannot be divided exactly by any number greater than half on n. For example, if n is 100, then n cannot be divided exactly by any number greater than 50. The first function would check even for all the numbers from 51 to 99, but we understand that it will be of no use. With this knowledge, we can improve this function, and this change will make our function execute at double the speed. A number, which is not prime, is known as a composite number. And there is a mathematical property that states that every composite number has a factor less than or equal to its square root. This means that a number will not be prime if it has a factor less than or equal to its square root. Conversely, this also means that if a number doesn't have any factor less than or equal to its square root, then it is a prime number. We can, further, improve our function with this knowledge. It means our for loop only needs to increment the value of I up to square root of n. This shall make our function execute very fast compared to the last two functions. These three functions are not different from each other in logic but just make use of mathematical knowledge. I wanted to demonstrate through these examples that studying a problem in depth can help us write better, faster programs. There is a fascinating technique known as wheel of Seive. We have been improving our function so far by limiting the upper limit of the loop. But we are trying to divide by all the numbers starting from 2 to that upper limit. If we check with 2 separately, then we need to only check if any odd number can exactly divide n. This concept is extended by wheel of Seive. The mathematicians have demonstrated that once we have tried dividing by 2, 3, and 5, then we can start division trial from 7 and we can keep incrementing in the pattern of 4, 2, 4, 2, 4, 6, 2 and 6. And then repeating the same pattern. Interested viewers can find tons of knowledge on this topic by trying to search wheel of Seive on the internet. So, a function written with this knowledge may look something like this. We keep the specified increments in an array. We check for 2, 3, and 5 separately. Further, we start our loop from 7 and we keep on incrementing by the value from the array. Once we have used all the 7 increments, we reset the counter to start using the array from the beginning again. The condition k into k less than equal to n is another way of saying that we want to check only up to the square root of n. This function skips over the candidate factors, thus, making our function even faster. If we perform a benchmarking of these methods, the performance of the last two methods is somewhat similar. The first approach is of course slower, the second approach does the job in exactly half the time as expected, but it is nothing compared to the improvement that we observe in the last two methods. Now, we move on finding all the factors of a number. Whatever we have learned so far, with that, our method to find all the factors of a number can look something like this. We execute our loop starting from 2 and going up to half of n. N by 2 will be highest factor of n. And if any numbers divides n exactly, then it is factor, and we display that factor in this method. In a real-life scenario, you may put all these factors in an array and return the array as the return value from this method. So, our first approach to find all the factors is a very simple one. Let us try to build on this one. Let us say n is 100. We check if 2 can exactly divide 100. Yes, it can. So, 2 is a factor of 100. When we divide 100 by 2, our quotient is 50, as 50 multiplied by 2 is 100. Therefore, 50 is also a factor of 100. Using this knowledge, we can optimize our code. The modified method may look something like this. If I is able to divide n, then I is a factor of n, and so is n divided by I. In the last, we need to check for an extreme case, as this condition may also be true. I leave an exercise for the viewers. Can we remove this extreme case by changing the condition in the for loop to I less than equal to limit? Another thing to notice is that we are computing the value of square root of n outside the for loop. In some languages, this may be more efficient than using square root computation directly in for loop condition. This brings us to the benchmarking of these two approaches. Have a look. Our first approach is drastically slower, in comparison to the second approach. The change that we have made seems innocuous, but the results demonstrate that it is a huge improvement. Let us move on to generating prime factors of a number. We have already learned to generate factors of a number. We can add additional check that if a number I is a factor of number n, and I is also prime, then I is a prime factor of n. The code can look something like this. With the additional knowledge that the prime factors can only be up to square root of n, we can even optimize this method further by changing the condition in the for loop to square root of n instead of n divided by 2. This method also shows the power of functions. Our code looks very simple and small because we are using function that we have written earlier. This is beginning of the modular programming. There is another interesting oddity of prime numbers. Beyond 2 and 3, the prime numbers always take a shape of 6 multiple of natural numbers, plus minus 1. For example, if natural number is 1 then potential prime numbers are 5 and 7, 6 multiplied by 1, plus minus 1. If natural number is 2, then the potential prime numbers are 11 and 13, 6 multiplied by 2, plus minus 1 and so on. There are numbers that follow this form but may not be prime. For example 25. 25 is 6 multiplied by 4 plus 1, but it is not prime. Keeping this oddity in mind, we can rewrite our method in this way. We keep on checking every number of this form beyond 2 and 3. We check if this potential prime is a factor of n and it is a prime number as well. This shall definitely be an improvement over the last method. Similar to last method, we can change the loop condition from divided by 2 to square root of n. Next approach is one of my favorite approaches. I like these kind of approaches not only from optimization point of view, but also from programming perspective. For example, we take a number, let us 100. We find its first prime factor. It is 2. We print 2 and we keep dividing 100 with 2 and subsequent quotients as long as it is exactly divisible. So, we get down to 25. We find the next prime factor of 25 and repeat the process of continuous division until we reduce it to 1. This technique is making use of the process that we learned in our early school days of factoring a number. We learned to write 100 in the form of 2 into 2 into 5 into 5. I would like that you try to write this method on your own, pausing the video here. Let me share the code for this method. As long as the number is greater than 1, find a factor of n, we display the factor, and we keep dividing n as long as it is exactly divisible. We try to find the next factor, by incrementing factor. In this approach, we need not check if the factor is prime, as the next factor will always be prime. This is how the factorization works. A very nice example of importance of classical programming problems. This technique teaches us that there are many ways to approach a problem, and whatever we learn at some stage will be useful later, if we understand it. The benchmarking of these three methods demonstrates what we expected all along. The second approach is much better than first approach, but our third approach is best of all as there is no overhead of checking if the factor is prime as well. This brings us to the problem that we started for, the largest prime factor of a number. I believe, with all these methods are learning, all of you can write that method. We write the method in the simple way where we keep on finding factor and we keep checking if the factor is prime as well. If it is indeed prime, we hold it in a variable. Once the loop is over, our last held value is the largest prime factor. Please note that we are executing the loop only up to square root of n, as a prime factor will always be less than or equal to square root of n. The second approach to find the largest prime factor of a number makes use of the factorization technique that we learned earlier. Rest of the program is similar to the last one. We find a prime factor, and we hold its value in a variable, largest. The last held value is the largest prime factor. There was nothing much to do in the actual problem, once we have learned the concept of checking prime number, factoring a number and so on. Looking at the benchmarking, we come to the same conclusion that we witnessed during the generation of prime factors of a number. The factorization technique clearly outperforms the other approach by a huge margin. I would suggest that you should try all these methods yourself, and choose the one that you like most. Please do let me know in the comments if you come across any other way of writing these methods. Do let me know which one you like the most. Thank you all of you for staying with me. Happy programming to all of you. Keep programming.